So the title of the talk today is Are Small Nuclear Reactors the Answer to Sustainable Energy for Canada? Not necessarily the world. And I thought you heard what I have done on the academic side, but I thought I'd give you a quick overview of what I've done on nuclear so you understand why I'm actually here today. I actually did my first 3 degrees in the University of Manchester, and one of my professors, Professor Smith, was one of the experts that guided the UK how to move forward in the nuclear program. So I'll age myself, so in the late 70s he was doing talks on nuclear power, and he actually was a big proponent of CANDU, reactor technology. And according to him, at the time, the UK would have probably preferred, he certainly would have preferred Canadian technology over what they eventually developed and bought. But the real problem was the sustainability of heavy water production and delivery to the UK. So they didn't want to be under the influence of Canada. They wanted to have their own technology. They went with AGRs. Because of that, and because of him, I got involved with forensic engineering, corrosion science, and with a view of moving to Canada. My 2 only relatives were actually at AECL. So when I moved to Canada, I wanted to get into nuclear. So I actually was working for Central Nuclear Services for 7 or 8 years in Ontario Hydro. Worked on a whole load of really high-profile projects, none of which I believe got a lot of public exposure for perhaps good reasons. One of them was the CANDU vault corrosion problem. Pickering A could have died in the 80s or 90s because basically the coolant system for their CANDU vault, which was the enclosure for the reactor, was like Swiss cheese. We came up with a solution for that. Another problem I worked with was the ion chamber support for, which looked at the reactor at low power. And I think it was the one and only time that the reactor could have been not in optimum control at low power, because with the ion chamber, the power level up to 20% was measured by the ion chamber. And the problem was it was a ton weight, it was at a specific spot, and with the lever it was on, if it moved in any way, the whole calibration would be thrown out, and the control systems could have been such that it would start pulling rods without really knowing what the power was at low power. So those are some of the projects. I'm very proud of the fact that I was probably the only person to ever have 2 40 by 10 trailer, R&D trailers, both at Pickering and Darlington, in the inside of the plant, where I was actually monitoring water flow and looking at flow conditions and corrosion. Always got me into trouble with the security at Pickering and Darlington, because I was always setting off the alarms with the fences and stuff. I did actually move on and work for 2 years in energy management. That's how I ended up in Waterloo. There was a Western region had a plant here that we basically gave out tens of millions of dollars in grants to make local industry, commercial businesses, and residential homes more sustainable, more efficient. So we were the award-winning group that actually did the best work in all of Ontario. I did that for 2 years. I left Ontario Hydro because they offered me a promotion to go back to Toronto, and I didn't want to go to Toronto. I liked Waterloo. I stayed in Waterloo. I had a problem, how to stay in nuclear. I ended up going to Babcock and Wilcox, and I'm taking up way too much time. So I worked in Babcock and Wilcox for quite a few years. I did supervise several really high-level, high-profile R&D programs there. But some of the ones that I've written papers on, about 40 refereed papers on welding, new steam generator alloys, chemical cleaning, chemistry, that sort of thing. I've also worked with the Electric Power Research Institute and worked with several committees on chemistry, Yucca Mountain, which is how to get rid of spent fuel, that type of thing. So I have quite a robust nuclear background. and have worked on committees that are organizing or technical committees, and did work for a large American consulting firm with PWRs. But in 2000, I joined the university as a research professor, and you've heard the rest. So I thought the way we would do this, first of all, please feel free to ask questions, and let's make this interactive. Being a talking head is boring. But the other thing is, because there's so much material in our talk, I thought I would do the history, and I think it's very important to look at the history of how nuclear evolved in Canada. And then I'll pass over to the real expert in small reactors, who is Jim here, who I had the pleasure of working for a number of years at Babcock & Wilcox. 32, discovered the neutron. 51, first commercial production using nuclear power. Basic MPD, 62, so like 30 years later, we had a proof of concept for CANDU in operation. And by the 70s, 25 countries had initiated nuclear power electric generation projects. The interesting thing, I think, from our perspective, a lot of the interest in nuclear power was fueled by growing concern for energy security. That seems to have changed a little bit in the last couple of years. In fact, in the last year, it's changed a lot. But in those days, in the 70s and 80s, huge issue of energy security because of, and also they were always worried about, I think you probably remember, some of us will remember, they were always talking about, and they had all these graphs, how fossil fuels and oil would run out by 2000 or 2010, whatever that was, and that has completely changed as well because of fracking and whatever. But there was really a huge concern at that time due to depletion of fossil-based fuels and increased oil prices, and the effects of environmental degradation. At the time before Ontario became nuclear, it was all mostly, you'd think, a lot of water, hydropower, but a lot of it was coal. Why the nuclear industry stalled. There was a drop in oil prices in '79, and the other thing was 3 Mile Island. Has anybody heard of 3 Mile Island? Yes. And obviously a lot of us heard of Chernobyl. That really put a damper on the whole thing in the 80s. And several countries, most notably France, though, continued to build their civil nuclear plants, and they became very reliant on nuclear power, France, around this time, and became a big player. And you start to see a shift, I think, around this time where America, United States, used to be a big player with Westinghouse, Babcock & Wilcox, GE. You see a shift going to Electricité de France and Framatome, and now they're a big player in the world. So this contributed to a relatively smaller global industry growth in the 80s to 2000, which is the time when I was actively full-time in nuclear. But I can tell you at that time there were several big issues in nuclear. One was life extension, because the licenses at that time were for 40 years, and there was a big concern about whether we could extend it for another 20 years to 60-year life. It all seems pretty common now, but at that time there was a lot of concern that you couldn't extend the life. There was real issue about, if you were in Ontario in the 90s, you were seeing a lot of demand-supply curves, which showed basically we did not have the supply to meet the demand, hence the energy management program. And basically a lot of issues that have changed in recent years. Nuclear industry overview, though. 31 countries producing nuclear power as of just now. 450 51 commercially operating nuclear reactors, an installed capacity of just under 400 gigawatts. Approximately 315 reactors were commercial operation in 19 OECD countries. And the area where we're seeing a lot of growth in nuclear is nuclear India and China, where there's 96 reactors in operation and 32 more under construction. I won't go through all this, but basically this gives you a bit of a feel for the players. Some of the interesting points in this would be that Germany has plans to phase out its nuclear. Sweden was supposed to phase out all its nuclear. Japan obviously has a lot of troubles because of Fukushima. And Canada has 19 reactors with 60% of the Ontario supply. Just throw this up, sorry if you can't read it, but obviously the most of the worldwide 451 reactors are PWRs. The green is BWRs, and basically the pressure, this one is CANDUs, fast breeders, and these are basically Chernobyl type reactors. Areas where nuclear power is #1 energy source, I think it's important to look at this. France, 72%, Ontario, 60%, Ukraine, 55%, and Belgium, Hungary, and Slovakia, all around 50%. And so obviously there are huge reliance on nuclear. France has spearheaded the use of nuclear power generation in the world. And it's really, you could see over the 80s and 90s, France taking over a lot of the research, a lot of the development away from what used to be in the United States. 3/4 of France's power comes from nuclear plants. Lithuania used to be 75%, but that was one plant, it's a small country. The other interesting thing is Pickering will close by 2024, so it'll go down to 50% reliance. So Canada. Canada has 75 years. It's got a very long history of nuclear. It was involved with the Manhattan Project prior to some of the things I'm talking about. Atomic Energy was formed in '52. Canada funded R&D programs since that very inception. And AECL has received commercial revenues from its ventures. I think some of the points I wanted to put here really was the situation in Canada was unique in that the federal government doesn't have control over power generation that the provinces do. And so there's always been this kind of problem of trying to promote nuclear in other provinces. And attempts to build their own, operate, like Gentilly 1, have failed. But basically, the big Ontario build program in the 60s and 70s was partly a result of the government of Canada having concern that Ontario had too much coal-fired fuel. And it ended up being a joint project that really worked well. So a timeline for just where the reactors have come up. The Pickering, 71, Pickering 2 and 4, 72, 73, Bruce 1 to 4, 76 to 78, 3 Mile Island accident, 79, Darlington, where I actually was very much involved with the new build. I actually was in the plant where there was always issues and problems. I very much worked at Darlington for a number of years. In fact, they wanted me to make me a plant metallurgist, which they've never had before. I was always a plant chemist. So in the 90s, Darlington, huge cost overruns, but that's another issue. But basically, you also saw a swing from AECL being very much involved with design and commissioning to, by this time, Ontario Hydro design and development, R&D, really looked after any issues to do with the building and issues with the plant. 99, Atomic Energy Control Board granted operating license for Maple 1. I'm sure you've heard of Maple 1 reactors, which started in 2000, 2003, but they were shelved in 2008. So that gives you a bit of a view of the nuclear thing. I think it's also important just to look at some of the timelines with AECL. 47 different reactors built. 6 research reactors were built for universities. The closest one would have been McMaster, I believe. It's done several development works in CANDU reactor types, but recently a lot of them haven't gone very far. And actually you'll see perhaps, I shouldn't even be getting into, now you're starting to see SNC Lavalin getting involved a lot more with some of this. Power generation in Canada. Canada's nuclear energy power peaked in '94. It dropped, and actually because of improved reactor performance and refurbishment, it's had a little bit of an uptick in 2005. There's been renewed interest in the nuclear industry. This has been spurred by increasing demand, particularly from Ontario, to a lesser degree, to comply with Kyoto, or the Kyoto, that was the push a few years ago. And the provincial government had plans to build several nuclear reactors and has been still advertising, and the union has been pushing for nuclear reactors ever since, but it's not going anywhere. All plans are deferred. I just threw this up, I don't want to get into it, but it gives you an idea of the sizes of the CANDUs. Basically, Pickering, 540, it was always regarded as being a bit small. Bruce, CANDU 6, Darlington, they're all sort of variations of CANDU 6s in the 700-800 range. They did try a CANDU 3 in the 80s, and that was for Saskatchewan, I believe, but it wasn't sold. CANDU 6 improved CANDU 6 went to Romania, Wilsung, and Kishan. I think there was plans for Argentina as well, but that never panned out. And all the other reactors that have been developed have never been sold. So basically, up until the 90s, early 2000s, life extension, the other thing was bigger, and better reactors. There's a big push for anything over 1,000 megawatts, 1,200 megawatts. There's even talk at one time of 1,500 megawatt units. Not CANDUs, but they were hoping in that space. So up until about 2000, everything was bigger, better, life extension, that type of thing. Ontario outlook. Obviously, Ontario dominates the nuclear industry. Contains 18 operating reactors, has refurbished 4 reactors. It exports a small amount of power. So the whole thing also around 2000 was, there was a real issue about transferring power from Hydro-Quebec into Ontario because of transmission issues. But now they're talking about exporting, importing power. But a portion of Ontario's electricity production from hydro is actually 22%. But there's all our issues with hydro as well. So Ontario's integrated power supply, 2007, Ontario Power Authority filed its first ever 20-year integrated power supply plan with the Ontario Energy Board. And it was similar to the Minister's supply mix. But basically the 3 points that came out of this was double the amount of hydroelectric power and all our renewables by 2027, slash peak demand by 6,300 megawatts. Part of the problem with Ontario has always been not the base demand, but the peaks and valleys, and trying to address when there's peak demand. And in the past, when there was not enough supply, then they had to import a lot of power. The other problem was with coal plant, they actually were not using as much coal plant as perhaps they wanted to because of issues with environment. And retire the remaining coal-fired plant by 2014. So that was the plan. So what's a small reactor? A small modular reactor is generally around 300 megawatts or smaller. It can be as low as 3 megawatts. Advanced inherent safety features can serve multiple purposes, including power generation, industrial heat building, heat desalination. And there's been a lot of talk about desalination in other countries. Smaller, simpler, cheaper, cost predictable, can be on-grid, off-grid, end-of-grid. So no questions? No? So I'll just hand over to the real expert in small modular reactors, Jim Smith.
Okay, my name's Jim Smith. I'm very pleased to be here talking to you today about small reactors. I have quite a bit of background in small reactors, and I'm going to surprise you a little bit by not coming here trying to sell small reactors to you. I'm going to explain the background and explain why it makes me see small reactors in the way that I do. Now, I've had pretty extensive experience both in the engineering and business aspects of nuclear, both in the CANDU area and in the pressurized water reactor area. One of the things that we did at Babcock and Wilcox was sell components such as steam generators, reactor heads, and whatnot to the PWR plants in the United States. It was quite a big business and got a lot of exposure there. I participated in some of the development work that Atomic Energy of Canada was doing on the CANDU 3 reactor. The idea of the CANDU 3 was it was half the size of the reactors being sold in Quebec, New Brunswick, and so on and so on. And somehow AECL felt that all the economics of scale could be turned upside down, and if you made something smaller, it would become not only cheaper on a proportional basis, but it would become altogether more economic. Well, that didn't turn out to be the case at all, and the CANDU 3 project ultimately fell apart. Now, the real first exposure for me was to a project that I was part of in 2010. It was put together by the Petroleum Technology Association of Canada, which is a group of pretty much all the big oil companies, and they have this technology organization in Calgary. And they asked the question, is it possible to come up with a nuclear device that will provide the steam for oil sands injection? And they had a series of requirements. Like, for example, they didn't want one big nuclear reactor doing this. They said, we have to have 24/7, 100% reliability. So what we want is 4 small reactors to cover effectively the steam production of 3 reactors running continuously. So it was, 3 plus a safety factor of 1. And one of their requirements was a requirement for very high steam pressure. Now, this became a problem for conventional reactors like pressurized water reactors and CANDUs. They didn't have nearly high enough steam pressure. But what we found was that there were designs out there for gas-cooled reactors that were in the right size range and could give the high pressure. That got us thinking, and with the other author of this study, a guy named Ralph Hart, who had spent numerous years at Atomic Energy of Canada, General Dynamics in the States, International Atomic Energy, and Westinghouse, and we kind of put our heads together and we created Northern Nuclear Industries Limited. And our real thought was, can we come up with this sort of holy grail solution of a small reactor that suits Canada's needs? So N2I2, which is Northern Nuclear Industries, we looked for a best fit, and we wanted something that met all these requirements of being able to be at the end of grid, off grid. What was the appropriate size? What were the issues? We looked at numerous reactor types. We even looked, it's not mentioned here, we even looked at a small miniature CANDU, and there were lots of technical reasons why it wouldn't work. We looked at molten salt reactors and so on. And what we ended up with was a lead-cooled reactor. It uses molten lead as its coolant, and it uses a type of fuel called a triso pebble fuel. The fuel is actually contained in things that look like billiard balls. The coolant flows through a bed of 50 or 60,000 of these billiard balls, and the heat comes from inside the billiard ball into the coolant. All of the work here was self-funded. We found absolutely zero interest in governments at that time to fund this kind of work, like zero. We talked to some private investors. no interest whatsoever. The issues were the length of time to produce a product. It takes forever to come up with something. Very complex project risks. You know, the whole thing can drive off the cliff at any point in time. Technology risks, licensing risks, it was just not the kind of thing that private investors were even remotely interested in. And most importantly, we started looking around at these potential markets, and we found, much to our surprise somewhat, that there was no interest in the market for very much the same reasons. You know, like if you have a remote community in the Arctic, they need power today. They need it in small quantities. They can buy a diesel generator. They can plug it in and start it up today. They're not interested in something they have to wait 10 or 12 years for. They're not interested in many aspects of it. And so all of a sudden we started to refocus and say, hey, are we just pursuing a ghost here? And anyway, we went on from there. But as we did our development work, it reminded me of something that was written a long, long time ago. It was actually written in 1953 by U.S. Admiral Rickover. He was head and master of the U.S. nuclear fleet. And, you know, we would consider it a big deal today for someone to be an executive of a utility with 10 or 15 reactors. He was executive of a utility with about 200 reactors. And he was getting very frustrated and made some of these comments to the US Congress. I'm not going to read them in detail. But he started categorizing reactors as either academic reactors, which are very easy for people to talk about. Like I could stand here and tell you that small reactors are faster, cheaper, lighter, all these wonderful features. But that's what he called an academic reactor. And then he talked about a practical reactor. These were the kinds of things that were being actually developed and actually built. And he said, there's a lot of confusion, and important decisions about the future development are frequently made by people who do not necessarily have the intimate knowledge or understanding of these things, but they have to understand certain things. And they find that there's confusion at every step. It's because of the difference between practical and academic reactors. So the summary of it all is, an academic reactor is simple. It's small. It's cheap. It's light. It can be built very quickly. Very flexible in purpose. Very little development required. It's all off-the-shelf parts. Nothing to it. It's at the study phase. Very importantly, it's at the study phase, not being built now. So here he was in the midst of a multi-billion-dollar, very complex development program of the propulsion systems for the US submarines and aircraft carriers. He started talking about the difference in a practical reactor. Number one, it is being built now. Number two, it's behind schedule. Number three, there is an immense amount of development work required. Even on repetitive types, every new model ended up with immense amounts of development work. It's very expensive. These guys say it's cheap. He says it's not just expensive, it's very expensive. It takes a long time to build. A lot of development work are required. And because there's so much development work required, every new problem that was not foreseen over here pushes back the schedule, makes it more expensive to develop. It's large, it's heavy, it's extremely complicated. So this is important. So just remember what I'm talking about here when I refer to academic reactors and practical reactors. Now, who's doing what around the world with small modular reactors? The Russians are quite active in it. They have some situations a little similar to ours. They have Siberia, we have the Arctic, and so on. They've actually been running 8 megawatt reactors since the 1980s. They've developed pressurized water reactors in the 300 megawatt range. They had developed a very interesting concept, which they call the KLT-40S. And they said, okay, it's very difficult if you have a community on the shore of the Arctic Ocean, very difficult to go in there and do construction work. So why not take what were basically submarine reactors, 35 megawatt PWRs, put them on a barge, float the barge to the location, park the barge, and then just hook up the electrical connections. That one also has desalination, I believe. But they didn't just talk about it, they actually did it. Took about 15 years, but this past year, the first barge-mounted plant was placed in Siberia, and it's now producing power. They have fast reactors. Without getting into the description of that too much, they tend to be more compact. These were developed for submarines using a combination of lead and bismuth as a coolant. It basically behaves the same as our lead coolant in the Northern Nuclear Industries reactor, but because it's a lead bismuth eutectic, it has a far lower freezing point. So we had a big issue of having to keep our reactor coolant above about 325 degrees C all the time, even during shutdown conditions, or it would start to solidify. With lead bismuth eutectic, that temperature gets dropped to about 125 Celsius. When you have submarines parked in the Arctic for long periods of time, keeping the reactor coolant hot is an issue. Argentina is building a 25 megawatt PWR, and it's going to start up this year. China, they are developing gas-cooled reactors. They're developing molten salt reactors. Now, the United States developed a molten salt reactor at Oak Ridge Labs in the 1960s. They abandoned it, even though it seemed to work reasonably well. But the United States just handed all of their Oak Ridge technology on the molten salt reactor to the Chinese. Said, here you go. If you can make something out of this, have at it. So they're going at it, but the Chinese molten salt reactor program is just still in the prototype stage, and they've already spent more than $3 billion on prototype development, even with all this Oak Ridge data as a starting point. So in accordance with Admiral Rickover, these things are very expensive. Korea has developed a 90 megawatt PWR. In the United States, there's a project called NuScale. They developed a 60 megawatt PWR. It was developed under a U.S. federal government co-funding program. They've burned through about $300 million of federal funding and funding from a bunch of other sources. And they haven't actually put a shovel in the ground yet, but they're already projecting that the first reactor is going to be $1.2 billion. BWXT, which is sort of part of the old Babcock and Wilcox, they're the people that make all the components and fuel and so on for the U.S. Navy program, the submarines and aircraft carriers. They took about $300 million of US federal funding and a bunch of funding from the state of Virginia, spent it trying to develop a 360 megawatt PWR, and when the money ran out, they stopped working and they just shelved the whole thing. They said it's a bridge too far kind of thing. Westinghouse developed a 335 megawatt PWR and they shelved it. They have a newer 225 megawatt unit, but they're not going very far with it. A, because they can't get any funding for it. B, they're effectively bankrupt right now because they believed some of these things about the advantages of modular construction and so on. They tried to apply it to some big reactor projects and put themselves in the poorhouse by doing it. General Electric has a very interesting reactor called a prism reactor, but it's only something that's on the drawing boards. It is actually designed to take used fuel already run through pressurized water reactors or boiling water reactors, reprocess and reburn the fuel, sort of recycling of nuclear fuel. Interesting concept, but again, it's never gone past the drawing board because it's expected to be phenomenally expensive. There's probably 20 or so additional startup companies developing small reactor concepts in the States, including one that's actually funded by Bill Gates. But he can see that there's a limit to what he can do, you know, multi-billionaire, but he's not going to spend billions of dollars on this thing. So that company called Terrestrial Energy is really just promoting a certain type of academic reactor. That's kind of where we are. And then there's basically nothing happening in Canada of any significance. However, here's what the SMR suppliers claim. They're simpler, they're smaller, they're cheaper. Now, Atomic Energy of Canada is trying to get a program going in Canada, and they're lighter. They have low pressure coolant. You know, like our lead, molten lead coolant in the Northern Nuclear Industries reactor basically was a zero or an atmospheric pressure reactor coolant. In a PWR, for example, the coolant pressure is say 15, 16 megapascals. So a big part of the safety analysis is what happens if you break a pipe and all this 15 or 16 MPa fluid comes blasting out of the reactor and it tears up the fuel and so on. So having an atmospheric pressure coolant makes it lighter. It's fast, it's modular construction. Well, that's what Westinghouse tried in some of their recent PWRs in the United States, and it bankrupted them. It's multi-purpose. Can produce power, industrial heat, desalination, and yada, yada, yada. But that was exactly what Rickover was getting at. He did not want to do that. He wanted to just focus on powering these submarines. Keep it simple in that regard. You can go to a prototype quickly. This is basically what the SMR people are claiming. Well, you can't, because if you start building it before you've engineered it, invariably this leads to delays. Delays result in increased budgets. You blow the economics of it. And of course, the SMRs are not being built. Well, the academic reactor, according to Admiral Rickover, simple, small, cheap, light, quick to build, flexible for purpose, little development required. It's exactly what these guys are saying. Now, some of the practical reactor aspects of SMRs. Number one, every SMR that's out there, even the one we were concluding for Northern Nuclear Industries, uses enriched fuel. Well, back way back in the beginning of the Canadian nuclear program, there was a decision made by the government of Canada that there will be no enriched fuel and there will be no fuel enrichment in Canada because of a stigma that enriched fuel is part and parcel of a weapons program. And we want to show the world that we are having nothing to do with nuclear weapons in this country. And the way to do that was no enriched fuel. Every SMR uses enriched fuel. In the Northern Nuclear Industries reactor, we were going to use this triso pebble fuel. It was definitely enriched. It had about 10% enrichment in it. But we were working with the Chinese. The same type of fuel that we were going to use, this triso pebble fuel, is what they're using in their gas-cooled reactor fuel, in their gas-cooled reactor plant. And they have built a factory to produce pebble fuel, so that's where we were going to get it. The US experience with SMRs, as I was saying, B&W spent $300 million of federal funds, Virginia state funds, and they abandoned it. NuScale, they haven't yet put a shovel in the ground, and they're already projecting the first 60 megawatt unit is going to be more than $1 billion. Interesting thing about licensing costs. Now, licensing is basically the whole process of producing the safety analysis, the environmental analysis, all the government-controlled stuff that has to be done in order to build and operate a nuclear power plant. In the US, they're estimating that a light water reactor, like a pressurized water reactor, boiling water reactor, the licensing cost alone is going to be $200 million. And furthermore, for these so-called advanced reactors, where there's no existing body of knowledge about how these things operate or what it's going to take to get through the licensing, they're estimating it's $1 billion process just to license it, if it can be licensed at all. A lot of things about these advanced reactors, while they seem attractive on paper, they go way beyond the bounds of what has been licensed to date. And they're seeing this as being a very complex and very expensive licensing process. All international licensing agencies basically run by the same playbook. So what you can count on is if the US, if it's going to cost this much in the US, for all intents and purposes, it's going to cost the same elsewhere. Now, some of the other practical issues are, in Canada, power generation is a provincial responsibility. Go to some place like Korea. Korea Electric has the sole responsibility for developing the power plants, building the power plants, operating the power plants, generating the revenue from the power plants, which pays for all the other stuff. In Canada, it's all different. You know, in Ontario, for example, Canada developed the design, but Ontario Hydro had to build it. Ontario Hydro had the big expenditures, but they generate the revenue from it. The old Ontario Hydro is kind of broken up now. Most of the provinces and territories in Canada don't want nuclear. You know, like ask someone in Alberta, do you want nuclear reactors in your province? And they'll say, forget it. They're perfectly comfortable with burning their own fossil fuels. And yeah, okay, the environmental aspects are unfortunate, and you know, they'll gradually work to remove them, but they don't want anything to do with nuclear. When you get into the territories, it's even worse. Because, like Nunavut, the Northwest Territories, very low population, very dispersed population, their provincial or territorial power generation authorities say, okay, I need power for a community of 500 people right now. I need it today. I can bring in a diesel generator and it can be fired up today. I don't want any part of waiting for some ill-defined, monstrously big project that will bring 2,000 construction people into my community of 500 people. It has to be run by outsiders, local people within the 500 community can fire up the diesel generator and everybody will be happy. They don't want it. The indigenous groups, and I have talked to them about this, they're concerned about safety, reliability, requirements for large amounts of outsider groups as operators of this thing, spent fuel disposal. This is a big one. They do not want to be a dumping ground for nuclear spent fuel. And what are the true costs? Construction, including modular, is very difficult and expensive in remote areas. This is what led the Russians to the barge-mounted reactors. Enriched fuel is an issue. Massive engineering effort on an all-new design. A lot of it is beyond ASME, American Society of Mechanical Engineering, nuclear code limits, mostly on temperature, but with these new reactors, you need new materials because of corrosion considerations. It can easily be dismissed as mere details, but they're the ones that kill you in the final analysis. Even if you're building this thing as a prototype, it still has to receive full licensing from the CNSC, hundreds of millions of dollars. The licensing process involves comparison to existing standards, and for these advanced reactors, the existing standards don't exist, so you got to develop them from first principles. The main beneficiary of this, now I don't really want to get into this, but if you pick up a newspaper at all these days, the name SNC-Lavalin comes up, and it's not in a very good light. And they would actually be the biggest beneficiary in this country of developing a small reactor. I'm going to show you why in a minute. But nevertheless, AECL, is Atomic Energy of Canada, is talking about a program involving 4 different prototype reactors. And I can tell you right now, this is a $10 billion program that they're talking about, just to prototype. Chalk River recently shut down its last large research reactor, which was called NRU. It ran more than 60 years. It was basically held together with baling wire at the end. But nevertheless, it shut down. And they have now hired a management consortium to run and decommission the Chalk River site. But putting new SMRs on that site would just extend their life by about 60 years and several $billion a year. Large reactors are being sold internationally currently at about $3,500 a kilowatt. For example, there's a project going on in the United Arab Emirates. It's being run by the Koreans. 4 1,400 megawatt reactors plus desalination. And this is a $20 billion project. It's on time, it's on budget, and the reactors will be starting up. I think the first one may have already started, but then it's 1 reactor a year coming online. Main power source for the Emirates. But the NuScale reactor, the small one in the States, is currently at least $20,000 a kilowatt. So you can see that it's way out of line, way more expensive on a dollars per kilowatt basis than anything in the large reactor area. Experience with small reactors at AECL is very poor. Almost no experience other than the Maple reactors, which were a failure. SNC-Lavalin was involved in a project in South Africa to do pebble bed gas-cooled reactors. It was a failure. It never got completed. We have to rely on foreign supply of enriched fuels, tens of millions of engineering hours, a lot of money wasted on this stuff in the past, and generally I have a hard time really buying into this current AECL project. So they have several reactor designs that have gone through a preliminary stage, and they're getting evaluations. Now, supposedly, these evaluations being done at Chalk River are being paid for by the reactor suppliers. But these companies typically are companies with only 15 or 20 employees, and they certainly can't do the engineering. They are using government grants and so on to pay for this AECL review, but it's all a review of academic reactors right now, so it's not costing that much. This is what I was talking about. If you go way back to the 1950s, and imagine all of the engineering in a nuclear power plant done by AECL, then it splits. The component design ended up with component specialists. Balance of plant, which is basically all of the stuff outside of the reactor building, you know, the turbine hall and all that stuff, ended up in the hands of a company called CANDU, which is a consortium. Balance of nuclear steam plant, this is the stuff inside the reactor building other than the reactor itself, also ended up with CANDU. Commercial nuclear reactor business selling CANDUs, although none of them were ever actually sold, but that's another story. That was all purchased by SNC-Lavalin in 2011. So what's left of the original R&D is the Chalk River, White Shell, etc. research and development activities, running research reactors, developing isotopes in research reactors and so on, but the last one just closed down. CANDU in 2004 ultimately became SNC-Lavalin Nuclear. So you see all of this, and this is now SNC-Lavalin. So if a reactor is built or developed in Canada, you can see that SNC-Lavalin is going to be the real beneficiary. Now, what is Atomic Energy of Canada these days? Well, this once huge organization is now 40 to 50 people, and they only have an administrative function over Canadian Nuclear Laboratories Inc., which is what's called a government GOCO, or government-operated contract, or government-owned contractor-operated company. The company running Canadian Nuclear Laboratories is CNEA, the Canadian Nuclear Energy Alliance, which is a consortium, and guess who's involved in that? So Canadian Nuclear Laboratories is approximately 3,300 employees as of this point in time. They get their revenues, most of their revenues are actually checks from the Government of Canada. Parliamentary appropriations, $826 million out of $918 million annual operating costs. Commercial revenue is less than $100 million, and it's been dropping continuously over the years. Big drop primarily from the loss of isotope revenues. They are spending a lot on decommissioning and waste management because the Government of Canada has a $7.5 billion liability for decommissioning all these sites. So they're spending money there, and these contractual expenses are everything paid to the CNEA consortium. In the area of nuclear science and technology, they're working on healthcare, environment, border security, cybersecurity, and clean energy. And this SMR program is contained within clean energy. And part of their program is AECL will work to understand existing capabilities, technology gaps, requirements, overall market interest. Like they say, they're going to go and beat the path again up to none of it and talk about, talk to local communities and so on. But that's going to be a dead end. And the commercial viability of these units, once they go from academic reactor to practical reactor, they're not commercially viable. Okay, so what's wrong with the AECL picture? Little or no interest in the market. Indigenous groups don't want nuclear. They just don't. Technology gaps are immense. CANDU was created due to this unique requirement in Canada to produce a reactor that ran on unenriched fuel. We're going to throw that away, supposedly, even though we have no enriched fuel capability in Canada. Is this sustainable? Well, in theory, you could give it a partial yes, because reactors don't emit CO2 gas and so on. However, the target markets are not interested. In theory, these things could be used to recycle existing fuel, but a small reactor, existing spent fuel, but a small reactor will not even make a dent in our backlog of spent fuel in this country. And we haven't answered the question of how to store the spent fuel in the first place. It could be considered renewable, I suppose, if you start burning spent fuel or burning plutonium or burning thorium, but that's a bit of a stretch. The government of Canada is on the hook for things like decommissioning the present nuclear sites such as Chalk River. But if you introduce new reactors onto the Chalk River site, even prototypes, that's just more in the liability area for another site that needs to be decommissioned down the road. These SMRs can be spoken of very positively by Atomic Energy of Canada, but they are still academic reactors. They're in the development stage, they're not being built, they don't have a clue what they're really going to cost or what it's going to take to develop them. The possible alternatives for the government of Canada, number one, I tried to illustrate this with the Russian reactors and so on. There's probably close to 100 SMR developments going on around the world right now. Why do we have to have a unique Canadian SMR? It's just ridiculously high expenditure, tremendous risk that the project won't conclude, like it won't reach a real conclusion. We developed CANDU because of a unique requirement of running a reactor on unenriched fuel. We don't have unique requirements here. Why not wait until somebody's got something suitable for us that we can just buy off the shelf and plug it in place? May not be till the year 2030 that you're ready to go on something like this, but it'll be designed, built, operated, tested, debugged, etc. And it'll be a somewhat reasonable price at that point. Focus the Government of Canada's efforts on other sustainable projects. Nuclear doesn't have to be the answer. Now, I've spent my whole career in the nuclear industry, and you could say, I could stand up here and say, well, nuclear is always the answer. Well, it doesn't have to be. And for some of our situations in Canada, it just isn't. It's just not a viable answer. If the government wants to pursue the SMR business, do it in such a way that it is at the expense of whoever's going to be the beneficiary, such as provincial utilities, developers, and so on, but not at taxpayers' expense. Adopt a position, so for the wise organization, our recommendation would be adopt a position that SMRs, small modular reactors, are not likely to be a good idea for Canada. AECL can carry on the present activities as long as it's done at the expense of others. Yeah, if they want to do some analysis of reactor physics in somebody's SMR design and comment on licensability and so on, that's fine, but let the developers pay for that. Market reviews. This should be expanded, especially when you're talking to the indigenous groups. This should be expanded to not just cover nuclear, but cover all possible sustainable alternatives. You know, wind plus storage, the existence of natural gas under the permafrost, geothermal, hydroelectric, energy storage, etc. There's any number of alternatives because nuclear on its own is going to prove to be a dead end. There should be no consideration whatsoever of actually building demonstration reactors unless and until there's an independent licensed operator identified and they're willing to take all the financial risks, including the eventual decommissioning risk. When Ontario Power Generation sells a kilowatt hour of electricity today, a small amount of that is set aside for every kilowatt hour that's produced. A small amount is set aside for eventual decommissioning costs. And that should be included in the real operating cost or operating risk of these prototypes. There should be an independent third-party oversight of activities. Like, what happens within AECL is they get so inwardly focused on how can this benefit us at AECL that they start losing sight of how can this benefit the ultimate customers. So put a third-party independent oversight in place to make sure that this thing remains beneficial to Canada and it just doesn't end up another huge multi-billion-dollar misadventure for Canada. Now, I don't want to really sound negative here, but you can probably get the picture that with the experience and exposure that I've had both to the overall nuclear business and particularly to the SMR business, I'm not very positive that this thing is going to end well for Canada. So I'm basically recommending stop it early rather than carry on with this thing. So the chances of this becoming a grand success are really pretty small. Okay. Any questions? Yeah.
SMRs, is it possible to do something without enriched uranium?
Well, we looked at that in Northern Nuclear Industries. Now, my former partner, Ralph Hart, now he passed away a couple of years ago, but he had spent many years at AECL. We started asking the question, is it possible to have a sort of a mini version of a CANDU reactor? And with a CANDU reactor, because you're running on unenriched fuel, you have to have exceptionally good neutron economy. Like, you have to make sure that all of the neutrons that are flying around are in the box, they're slowed down to thermal neutron spectrum speed, and so on, which is why you have the heavy water moderator and heavy water coolant and so on. And one thing that creeps into it is a concept of aspect ratio, like how big is the tank in diameter relative to how long it is. And you have to sort of maintain that aspect ratio as you try to shrink the whole thing down. So you're not only shrinking down the diameter of the tank, but you're shortening the fuel channels. And when you get to a SMR, you're down to a fuel channel that has like one fuel bundle in it and inside of a small tank. And then the neutron economy just starts to run away on you. And even in a CANDU type heavy water reactor, you actually end up having to enrich the fuel just to make it work. And way too many control rods and so on and so on. It just didn't seem feasible. Yeah.
You had shown that there was lead coolant was one of the options.
Yeah.
Did I misread, but was there also sodium coolant?
Yes, that has been proposed as a coolant like molten sodium, primarily in fast reactors. Now, fast reactors, you try not to slow down the neutrons because you want fast neutrons for a reaction with, for example, uranium-238, possibly plutonium can be thrown in there. This is an aim at really compact reactors. One of the practical difficulties with this is that if you have a molten sodium loop combined with a steam loop and there's any leakage, sodium and water, boom. And in this day and age, I mean, we all saw the videos of Fukushima. We all remember that view of the big boom. So deliberately designing the thing with something that goes boom is a very, very difficult thing to sell.
Yeah, that's why I find it a little unusual that you use sodium to cool, because sodium is very reactive.
Yeah, yeah, and that was one of the reasons why we didn't even consider it in Northern Nuclear. Now, lead doesn't react with anything, basically. We would probably have ended up having to separate two different isotopes of lead because one is more neutron friendly than another, and to allow us to have full operating flexibility in the thermal neutron range, we required a graphite moderator in there, but lead and graphite don't react, lead and water don't react. But we could optimize the neutron efficiency by separating lead into two different isotopes, and to be honest, we didn't quite know how we were going to do that. Nevertheless, yeah, lead was attractive because it's not a reactive material at all.
Jim, I guess one last.
Yeah.
It seems like a lot of different countries have worked on developing their own reactors, and it seems like there's tens of, or even more than that, of different kinds of reactors, and a lot of them have failed. Yeah. Has there been any work to make a collaborative project to make one good reactor, and everyone kind of uses that, sort of similar to ITER? Yeah,
well, actually, I'm glad you mentioned ITER because that is exactly what was done there. Something like 35 countries got together and agreed to cooperate on the building of a fusion reactor device. Now, fusion is, of course, the opposite end of fission. Sorry. In fission, you're breaking down a large atom into smaller things. In fusion, you're putting together very small atoms, fusing them together, and there's a big energy release from doing that. It's been shown theoretically to be possible. This is basically what fuels the sun, is a big fusion reactor. So you create an enormous heat, an enormous amount of energy in these sort of bursts inside something. The temperatures are so high they have to be contained in an electromagnetic field, because you can't have direct exposure to any of the materials, because we don't have a material yet that can withstand those temperatures. Complex, but yet possible. Now, in the 1990s, there was actually a very good case made for building the ITER reactor in Canada. They had a site picked out, which was next door to the Darlington nuclear plant. They had oodles of power available. Like, basically in a fusion reactor, you need a tremendous buildup of power to ignite this reaction and get it going. They had oodles of power. Darlington, 4 900 megawatt plants. Fuel is a combination of deuterium and tritium. Deuterium, we've got lots of it. We can get it from our heavy water supplies. And we have a big surplus of heavy water. Tritium, in Canada, we got loads of it. It's a waste product of a CANDU reactor. They have a tritium extraction facility at Darlington to remove the tritium from the heavy water. And you know, in places like the United States, they've built entire production reactors, billions of dollars, just to produce thimblefuls of tritium. We won't export it to anybody because tritium is actually used in nuclear weapons. So we don't export it. But if you imagine, had we put the ITER project on the Darlington site, we had the power, we had the tritium, we had the deuterium, and we would have attracted about $20 billion in foreign investment.
There's a lot of government support. Other countries were supporting it.
Yeah, and the fact is, the cost of the project would have been about 1/2 had it been built in Canada. We didn't end up getting it. Now, it's kind of a long and nasty story of why we didn't get it, but it had a lot to do with Atomic Energy of Canada basically saying, look, there's only so many nuclear dollars to go around in this country, and we want them all. And the Chrétien government, first of all, said, okay, if all our nuclear dollars are going to AECL, then we can't make the necessary input to the project, and the project moved to France. And then after that, the Paul Martin government pulled out of it altogether. So now they have an ITER project, 35 countries involved, not us, and they seem to be on their way towards first power by maybe 2024, 2025, something like that. And there's been about $20 billion spent on it, and all that money's flowing into France.
How much power will they be making?
It's hard to say because it's going to go in sort of shots. It's not really supposed to be a power-producing plant. It's just they will take away the energy in terms of heat and so on and so on. They'll go short bursts and so on. But basically, the state they're at is to demonstrate that they can continuously produce heat. You know, one of the things with a fusion reactor is it has no hope of being economical unless it's like big, you know, 1,000 megawatts or larger when it actually gets to the point of producing power. It takes an enormous amount of power to heat it up and fire it up and get it going. But if you can get it going in a sustained fashion, even if it's bursts of power, the heat taken out into an energy storage system and then turned into electricity from there, it'll probably be 1,000 or maybe even 1,500 megawatts.